Hello. We're going to continue our discussion on the Mathematics of Finance, Chapter 5. We're going to start into Section 5.3 today. Last time we talked about compound interest, and before that we were talking about simple interest, and now we're going to talk about annuities, loans, and bonds. A typical defined contribution pension fund works as follows. Every month while you work, you and your employer both deposit some amount of money into an account. The money is earning compound interest from the time it's deposited until you retire. The account continues to earn interest, but you are now receiving money out of the account. So it's a reducing amount. As you continue through the years and you're receiving more and more money, the principal value is being decreased with every payment out to you. So we considered this account as an annuity. During the deposit period, we call it a sinking funds problem because we're sinking money away. Now this is unlike compound interest. Straight compound interest problem, because instead of having a lump sum that we're depositing that is then earning interest, we're actually changing the principal in addition to the fact that the interest is getting reinvested. So this would be the same payment at the same frequency throughout the sinking fund period. So when we talk about an annuity, we are talking about an account from which you make withdrawals. So the annuity would be during the withdrawal period. During the deposit period, we will call that the sinking fund. It's generally used by businesses or governments to accumulate money in order to pay off some anticipated debt. So maybe they've borrowed money up front and then slowly they're building up an amount so that they can make a balloon payment at the end of the debt period. So here's an example of sinking funds. We're going to talk about how the formula gets derived, where it comes from. If we were to make a payment of $100 at the end of every month into an account that earns 3.6% interest per year, compounded monthly, that means that our investment is earning, we have to adjust that for the per month, so we're going to take the annual 3.6% and divide it by 12 for the number of compounding periods in a year, and that gives us 0.3% per month. Alright, so we can write that as I. Remember we talked about I in the last section, and that was our per period interest rate. So that gives us 0.003. This is the decimal form of 0.3%. Remember, whenever you're converting from a percentage form into a decimal form, you're going to move your decimal place 2 places, or if that's confusing, you can take the value and divide by 100 and it'll automatically move the decimal points for you. We're being asked, what is the value at the end of 2 years? So we can think of this separately. All right, so the first deposit, each is going to earn interest from the time it's deposited, and the total amount accumulated after 2 years will be the sum of them all. You're going to just add them all up. So over the course of the 24 months, you can see here we've taken $100 and we've added it up, and from month 1 to month 24, this is how much money we made. For month 2, we're going to deposit 100, and between month 2 and month 24, this is how much money we've made. Same thing here. You'd continue to do this all the way up to month 24, and then I would just add up those values. Now you're not going to do these manually. This is just showing you where the formula comes from. So when I added up all those values, you can see I've done that here. This ends up converting over to this well-known formula, and in this case x would be equal to 1 plus 0.003. Alright, so that means this x would be replaced by this, and this x would be replaced by this as well, all the way through. In our case, we end up with $2,484.65. So this is our formula that we're going to use based on that derivation. All right, so we were able to find the value by doing 24 individual calculations and then adding them up. This would be the formula that we're going to use. So just like when we were doing simple interest, FV is future value. It was the same for compound interest. N is still going to be equal to the number of total compounding periods. So that is going to be the equivalent of MT, where M is the number of compounds per year and T is the number of years for the investment. Now don't forget, if your time is less than a year, you have to convert it over to years. So if you were told it was 6 months, that would be a half a year. If you were told it was 3 months, that would be a quarter of a year. T is always in years. All right, I is going to be my per period interest rate. So that was the annual rate divided by the total number of compounds in 1 year. Now we have a new variable here. It's PMT. We haven't used PMT. PMT just stands for payment. So this is the set amount that I am paying into this account, that I'm depositing every whatever the frequency is. The frequency of my deposits will be the same as the frequency for my compounds. So if I'm told that it's compounding annually, that's once a year. If I'm told, that means I'm making one payment a year as well. If I was told it was monthly, it would be 12 times a year. That means I'm going to make monthly payments or deposits into this account. So here's a quick example. What would a problem like this look like? At the end of each month, we're going to deposit $50 into an account that earns 2% annual interest compounded monthly. Now, if they hadn't told us that it was compounded monthly, or they hadn't told us that it's at the end of each month, you only need to be given one. For our case, all of our problems that we're going to do, the deposit period and the compounding period is going to be the same. So if they do not give you one of these bits of information, you can get it from the other. So to find our future value after 5 years, we first are going to calculate I, which is the rate divided by M. So 0.02 is my 2% interest rate as a decimal, divided by 12, which is my number of months in a year. And N is going to be MT. So M is my total number of interest calculations per year, compounds per year, and 5 is my number of years, so that gives me 60. So now I can plug that in, plus my $50 payment, into my calculator, and I should get $3,152.37. Now, one thing we want to remember, and I may have mentioned this in class, is that the numerator here is a little bit complicated. So you want to make sure that you put parentheses before this initial parenthesis and after this -1. Otherwise, the calculator will not do it properly. All right. If you want, you can also put a set of parentheses around your denominator. It is just doing division, so it should work out okay. But I always like to have more parentheses rather than too few sets of parentheses. And this is 50 times this fraction. So you might want to take your calculator and make sure that when you plug this in, you are getting this value. If you're not, come see me after class and we can go over what you're doing wrong. Okay, so here is a little bit more complicated of a problem. In this case, we have two things going on. We have a retirement account that already has $5,000 in it. Maybe we switched, rolled over money from one account into another, or maybe we got some bonus that we had deposited into our account at the beginning. But in either case, we have a lump sum of $5,000 already in our account, and we're earning 5% interest per year compounded monthly. Each month for the next 10 years, we're taking money out of our pocket and putting it into this account, $100 every month for 10 years. And the question is how much money is there in the account at the end of those 10 years? So we've got two things going on. We've got a sinking funds problem for the $100 a month over 10 years, and we've got that $5,000 lump sum that was already sitting in the account cooking at 5% interest per year, interest compounded monthly each year. So I'm going to first calculate out my sinking funds problem. So I've got PMT is $100 per month. I've got a rate of 5%, so that's going to be 0.05. I've got M, which is my number of compounds in a year. That's going to be 12. And I've got I is going to be my R over my M. So that's 0.05 divided by 12. And I would just leave it like this. You can calculate it out, but I would carry 4 decimal places just to make sure that it doesn't have any rounding error at the end if you want to convert this over to a decimal first. And then my N is going to be MT, which gives me 120. Now, if I want to calculate how much money I have in the future using these values that I just calculated, I'm going to take my $100 payment, my I that we just calculated, my N that we just calculated, and I'm going to plug everything in. Now when you plug this in, don't forget my numerator, we want to put parentheses around it, so that way it will calculate this before it does the multiplication. And then my denominator, you can put that in parentheses as well so that it doesn't mess up your calculation. You should get $15,528.23. If you're not getting that, come see me and I can figure out what you're doing wrong, because this is crucial that you get the right answer. You have to put it in properly. So that took care of the sinking funds portion. Now the $5,000 that was already in the account, that's just a straightforward compound interest calculation. So we've got $5,000 that was already in the account. We know that we're compounding monthly. It's the same interest rate, our 5%. So we're just going to use the compound interest formula that we used in section 5.2. So when I plug everything into my compound interest formula, I get $8,235.05. So that's how much money I have over that time frame from my $5,000 that I started with. If I add the two of them together, that will give me a total amount, principal and interest from all the investments and the amount of interest over those years for 10 years of $23,763.28. So for these types of problems, you need to be really careful with the reading. It's a two-part problem, so you're going to break it out into the 2 parts, do all the calculations, and then you're going to add them together at the end. Sometimes we know how much money we want to have in the future, and what we need to find out is what is the payment that needs to be made per period at this set frequency, so that I can have that much money at the end, so I can make that happen. So this is the same formula, but it's solved for PMT. So it's the future value, it's a present value formula. It's solved for PMT. So this will tell us how much money we need to put aside each frequency that we've discussed, whether it's monthly, whether it's annually, whether it's quarterly, daily. And then we'll know what the future value is. We'll have our I and we'll have our N. We plug everything in, and that will give us our payment. Okay, annuities. As I said before, annuities are during the drawing part of the period. So this is when I'm making withdrawals. Just like before, we talked about where the formula comes from and logically how it comes about. So we're going to do the same thing here with the annuities, going over this scenario. If we were to deposit an amount, present value amount, of a certain amount today, earning 3.6% interest per year, compounded monthly, starting 1 month from now, we're going to start withdrawing money. We're going to withdraw $100 every month. So what's going to happen is, although we are earning interest, we're not earning $100 worth of interest. So the present value each month will be less. Okay? Eventually, we'll make our last withdrawal and we'll have nothing left in the account. All right, so we're looking to draw it down to exactly $0 in 2 years. So just like before, we need to calculate I. That's going to be R over M. So we have our 0.036 divided by 12. That reduces to 0.003. We have our payment. We know our payment is 100. So the first payment of $100 is made from a month. So the present value is $99.70. And when we make the second value, the second payment, 2 months from now, it has a present value of $99.40. And then we could continue that for 2 years, and we'd receive that last payment, which is going to tell us that we have a present value of $93.06 on that, and that would exhaust the account. So using our little number line that we had before, we can see that here's the first month, second month, third month, all the way up to the last month when we've completely exhausted all the funds. Now you're not going to have to do that manually. All right, so here once again we've found the summation that works for this. But in our case, what we end up with is this. If we've taken all the values and added them up, we get $2,312.29. So what does that mean? That means if we deposit that much initially, the bank will send us $100 per month for 2 years, and we'll have $0 left. Now the formula with the variables looks like this. So I've got my present value at any one time is going to equal the payment amount that I'm receiving times this fraction. So the numerator you're going to once again want to put inside a parentheses. It's 1 minus 1 plus I to the negative n all over I, where I is R over M and n is MT, just like it was for compound interest formulas. So this is the same formula. So that means if we're receiving a payment at the end of each compounding period, the account will be drawn down to 0 in T years, or after n periods, which is MT. That gives us the total number of periods. So here's a quick example. At the end of each month, you want to withdraw $50 from an account that earns 2% annual interest compounded monthly. So that means I've got $50, that's my payment. I've got my rate of 2%, so that's 0.02, divided by 12 because it's 12 periods per year. And then my MT is 60 because it's 5 times 12. And when I plug all that in, I'm getting 2852.62. Now once again, try plugging this in and make sure you're getting 2852.62. If you're not, you're probably not calculating this right. So you want to put parentheses around this whole numerator, which will force the calculator to do the numerator before it does the multiplication. And you also want to put parentheses around this, and that way it won't mess up your denominator. All right, so here's a couple notes that I've made here. If you're making your withdrawals at the end of each compounding period, we have what's called an ordinary annuity. If we're told we're making withdrawals at the beginning of each compounding period, we have what's called an annuity due. And what does that mean? That means that if you're withdrawing money at the beginning of the compounding period, you don't earn interest on the full amount so you lose interest on that payment amount because you've withdrawn it before the interest is calculated at the end of the month. So the formula changes slightly. All right, you're going to end up with payment times 1 plus I times this numerator divided by I. So if it says that the payments are made at the beginning of the month, your withdrawals are made at the beginning of the month, this is the formula you need to use. Now if I take the ordinary annuity formula, the present value formula that we just had on the 2 slides ago, and I solve for PMT, this is what I would get. So this now gives me an equation where I can calculate how much money can I withdraw over that time period given a specific amount of money that I have at the beginning of the draw period in order to draw it down to $0 by the end. And that's where I'm going to end it.